Matrix terminology and special matrices. Matrices and parts of matrices. We start with a system of linear algebraic equations, and it becomes intractable when we have a very large set of equations. Imagine having even just 50 equations with 50 unknowns, and imagine having to write that every time, and then we start doing algebraic manipulations. That's not really feasible. And in fact, 50 equations is very small. Much more common, it's hundreds of thousands of equations with hundreds of thousands of unknowns. So we need to do something different. And this is where the concept of matrices comes in. And so our system of linear algebraic equations is written in a much more compact, condensed form called matrix form. And our coefficients, these known constants, these A's, get folded into a, well, I'll call it a square matrix. It's a square matrix if we have the same number of equations as we have unknowns, but that can vary. So this A matrix can become a rectangular matrix. All of the unknowns, x1, x2, all the way up to xn, that is stored in a column vector. So the A matrix is square or rectangular. The unknowns are stored in a column vector. All of the constants on the right-hand side of the equation are also stored in a column vector. Now, again, it's a little bit tedious if we're going to write it this way to keep writing all of the elements in that matrix. So instead of writing all of these elements inside the matrix, we might just write it as a capital A inside square brackets, and the square brackets to remind us that that is a matrix. Or a notation I actually prefer is a bold A, because I think of the bold letter as it's bold, it's fat, it's containing a bunch of stuff, so it's a matrix. But other people use bold notation for other things, but I do tend to like this because then it also reserves my square brackets for using in equations to go along with parentheses and curly braces. And so our column vector we would write as an X inside square brackets or a bold X, and our column vector of constants also written as a B inside square brackets or a bold B. Another notation that I tend to like to stick to, and sometimes I'm forced to deviate, but what I like to do is use capital letters for square and rectangular matrices and lowercase letters for column vectors or sometimes row vectors. So that's my notation that I will use throughout this course. And to me, there's no difference between these two notations, and I switch back and forth, I guess, depending what mood I'm in. So we have our matrix here, and we can look at rows in this matrix. And the convention for linear algebra is to call this first row, row 1, our second row, row 2, and row 3, and row 4, and so on if there's more rows. Likewise, we can also talk about columns. So column number will start at 1, and then as we work towards the right, we have a column 2, a column 3, and a column 4. We can also talk about the diagonals of the matrix. And the most important diagonal is the center diagonal, and we'll call that the 0 diagonal or diagonal 0. As we go upward, we'll have diagonal 1, diagonal 2, diagonal 3, and if it were a larger matrix, that would keep going. As we work down, we have diagonal -1, -2, -3, and this would keep going if it were a larger matrix. So we have rows, columns, and diagonals. So sometimes we just use the word the diagonal, and that always means the center diagonal. So if you ever hear the diagonal, they're talking about the center diagonal. Sometimes the elements along the center diagonal are called the pivot elements, and that comes in algorithms that involve pivoting, and that's something we'll talk about later. Special matrices. We can have a matrix and we can call it symmetric. That means the numbers on either side of the center diagonal, the diagonal, are the same. We see we have 2's in the same place, if you will, on either side of the diagonal. We have 9's symmetric about the diagonal. We have 5s, and then we have 4s symmetric about the diagonal. We have 8s symmetric about the diagonal, 0s symmetric about the diagonal. So if we can literally just fold that matrix around the diagonal and see the same numbers, we call that matrix symmetric. We can talk about a diagonal matrix. So if we say a matrix is diagonal, or a diagonal matrix, we're talking about a matrix that has all zeros except numbers running down the center diagonal. If there's numbers anywhere else, we cannot call that a diagonal matrix. We have the identity matrix. The identity matrix is the closest thing to the number 1 that matrices would have. If we take any matrix, multiply by the identity matrix, we get that matrix back. And it is a diagonal matrix. It's all zeros except we have 1s going down the diagonal. If these are anything but 1s, or we have anything else out here on the off diagonals, that's not an identity matrix. The zero matrix. That's simply a matrix full of all zeros. So any matrix times the zero matrix equals 0. And so we call that the zero matrix. We might have what's called an upper triangular matrix. In an upper triangular matrix, we have all zeros except numbers filling in the upper triangular of this matrix. And if you remember from previous lectures where we saw a case where we kind of had this triangular shape, triangular matrices are like almost solved systems of equations. And typically if we have a triangular matrix, it's incredibly fast and efficient to solve that. So triangular matrices think of as almost solved matrices. Similarly, we can have a lower triangular matrix and a very similar thing. This represents an almost solved system of equations. A banded matrix. Banded matrices are 0 everywhere except there's a few diagonals containing numbers. And so the number of diagonals that contain numbers, we would call the bandwidth of the matrix. In this case, the bandwidth is 3 because we have numbers going down 3 diagonals. Sometimes we would also call that a tri-diagonal matrix. Then there's a Vandermonde matrix, and we will actually be constructing these when we start doing polynomials and curve fitting to polynomials. Vandermonde matrices, they're known to be ill-conditioned when the matrix size gets large, and of course there's known ways to mitigate that. But for us, when we're curve fitting to polynomials, we're going to have very small Vandermonde matrices, and so no problems will arise for us. But in a Vandermonde matrix, we have the first column's all 1s. The second column is whatever numbers these numbers are. Then the third column is the first column squared. And then the fourth column would be the second column cubed, and then the fourth, and then all the way up. So it has that type of symmetry to it. And in fact, this first column, we can think of as the second column to the 0 power. We all just get 1s. However, sometimes if there's 0 to a 0 power, we run into some issues. So when I'm building this type of matrix, I would just manually put 1s here, then insert this column vector, then that column vector squared, that column vector cubed, and so on, all the way to the end. Block matrices. Block matrices we can think of as matrices of matrices. So imagine we have 4 little matrices. We can build a big matrix out of these 4 little matrices. So F in this case would be a block matrix. I use this all the time, and I see a lot of people, they do a lot of very complicated derivations and come up with some really confusing equation, and they say, this is the matrix that you have to build. And I don't like that because that confuses me. And throughout the methods that I develop, I always like to figure out how to build small, simple matrices and then build the big matrices from those small, simple matrices. And very often that's even a simple step, even though in the end, I end up with a matrix that's maybe very complicated, but it's built in a simple way. So I use block matrices all the time, and it's a wonderful way to think about matrices. Sparse matrices. This arises all the time. In fact, most of the time we're doing linear algebra, our matrices contain almost all zeros. There's only certain places in our matrix that are non-zero. And so this would make absolutely no sense to store all of these numbers as double floating point numbers. We don't want to do that. That's inefficient. So a sparse matrix is still a matrix. It has all the same rules as a matrix, but instead we only store the non-zero elements. And so by doing that, we not only have to store what the number is, but where it goes in the matrix. So there's a little bit extra information. So if we were to actually take a matrix that had all numbers everywhere and store it as a sparse matrix, it would take up a lot more memory than just storing the full matrix, because we have the elements and where they are. But it is incredibly efficient for matrices that are almost all zeros. Take this type of matrix, for example. Right now, it looks like it's maybe 5% full of numbers, and that's because the matrix is very small. In a much more practical scenario, we would have matrices that are 100,000 by 100,000 elements. And if we have numbers only going down 2 of those diagonals, suddenly that matrix becomes 99.99% empty. And so that's very efficient to store as sparse matrices. And so we will make extensive use of sparse matrices when we start solving ordinary differential equations. So the opposite of a sparse matrix is a full matrix. That's where we don't have to store the positions of the elements. We just store an array of elements. And so we'll use this when it's mostly full of numbers and not mostly zeros. Size and shape of matrices. This is maybe a little bit unique way to look at things, but this is what's in my head, and I find it helpful to me. And we look at a matrix equation, and I'm visualizing the A matrix this way, the X matrix this way as a column vector, and the B matrix like this. And right here, we have a square matrix, so we have the same number of equations as unknowns. This is the most usual case, and there's lots of things in physics and science that reduce to this. We can get this from circuit theory. We can get this from solving differential equations or systems of differential equations, and it has an exact solution. There are times where we have more equations than we have unknowns, in which case our A matrix is rectangular and it's tall, but not as wide horizontally. Our column vector on the right is tall, but it's still just a column vector. The column vector that's multiplying our A matrix is shorter than the B matrix over here. So this can happen sometimes if we just have a few samples and we still would like to solve it, and it is still possible to solve, but we have to solve this in a sense of it being a best fit. So in fact, there may be multiple solutions, and just depending on what requirements we have, we could determine one of those is a better fit than another. And so anyway, we look at this as a best fit. And so we'll be doing this later when we fit curves to data. We'll have a whole bunch of samples, there's noise in that, and we determine a best fit and fit some kind of function to that. So curve fitting is a place where this arises. The other thing can happen. We can have more unknowns than we have equations. And we look at this and think, well, we don't have enough information to solve this problem. Well, in a way, you're right. We don't have enough information to solve it exactly, but we can do an optimization. There's probably multiple solutions. And again, if we have some kind of other constraints, we can play with these unknowns until it's satisfied and satisfy these other constraints in a way that gives us an optimal solution. So optimization problems have this type of starting point. So I don't know, this is very useful to me to kind of look at the size and shape of matrices and realize this is going to take us in different directions in terms of how we look at it and how we solve it. Health of a matrix. I think the health of a matrix is best done by examples. So I'm throwing out here 3 equations, 3 unknowns. I am writing both the algebraic form and the same thing in matrix form. And so I asked the question, is this system of equations solvable? And solvable exactly. This system of equations is not solvable exactly. Notice that the second row is exactly the same as the first row. So our second equation is not contributing any new information to this. So it's not solvable. Okay, What about this system of equations? And again, I'm writing the algebraic form, and I'm also writing those three equations in matrix form. Is that solvable? Now, maybe it took a bit to realize, but in fact, the second equation is just 2 times the first equation. So the second equation really still is the first equation, and it's not providing any more information. So this is still not solvable exactly. All right, here's another example. And system of equations, that same system of equations in matrix form, is that solvable? The answer is no. Now, this is getting harder to see what's going on, but notice that the second equation is simply the sum of the first equation and the third equation. Maybe you didn't notice that, but now that you notice it, that second equation is still not contributing any new information to this. So it's just like having 2 equations with only 3 unknowns. It is still not solvable. So I would call all of these matrices unhealthy matrices. They're ill-conditioned matrices. Okay, is this system of equations solvable? No. Notice there's an entire column here of all zeros. There's no information about y anywhere. So how can we determine what y is? So that system of equations is not solvable. So we went through a whole bunch of cases, and we also saw where maybe it's not immediately obvious looking at the matrix to see if it's solvable. So how do we know if a problem is solvable? Well, first, all the rows have to be linearly independent. So we can't have the second equation being the first equation plus the third equation, and we can't have the second equation being 2 times the first equation minus 7 times the third equation, because it doesn't provide any new information that way. So by having all rows linearly independent, that ensures that each row is contributing new information to the problem. Likewise, we can't have a row that's all zeros because that would not provide any new information. Even though that may not be an integer multiple of other rows and columns, it's still not providing any new information. We can't have any columns that are all zeros because that ignores information from whatever of the unknowns that column corresponds to. So we can't have any columns that are all zeros. So do we really want to check for all these each time? It turns out there's a very simple test. If we have a matrix equation, AX equals B, what we will do is calculate the determinant of that matrix A. If it's not 0, then we have all the rows being linearly independent and we can solve that problem. If the determinant equals 0, we have troubles. Now, that doesn't mean it's unsolvable. It just means that it throws us either into optimization or best fit sort of thing. So it's still possible to solve equations, but we can't say that we can just solve it directly and exactly. Okay, is this system of equations solvable? Let me point something out. So we have our first equation. We have our second equation, which is actually very close to the first equation, but I've changed these numbers a little bit. So this second equation is linearly independent of the first equation. However, it's very close. So the conclusion here is technically this is solvable. And since we're only 4 digits down, we could say this is probably even easily solvable. However, we might expect that answer to be a little touchy and unstable. So in other words, if we just change one of these numbers by a little bit, instead of being 1.0001, we put in a 1.002, the answer we get might change radically. And so we call that an unstable solution. And we would have to call this an ill-conditioned matrix, simply because the second row is so close to the first row. Even though technically it's different, it's close enough that it's ill-conditioned. And the closer our rows get like this, the more ill-conditioned, the less healthy it will be. So we can determine all this by what's called the condition number of a matrix. And this is a measure of, let's say we make small changes to our matrix. What kind of changes do they produce in the answer? If small changes in the matrix produces big changes, that's an ill-conditioned matrix. We would expect that to have a very high condition number and also less stable solutions. Now, where this comes in, if we're solving them directly with things like LU decomposition, it's usually not as much of an issue. But if we solve the system of equation iteratively, if we have something that's ill-conditioned, those iterative methods cannot converge at all, or it can take many, many, many thousands or millions of iterations to converge, if they even do. And I'll mention there's actually a rigorous definition for the condition number. We can determine the singular values of a matrix, and singular values are almost eigenvalues. We can kind of think of it as a diagonal form of a matrix. But anyway, if we take the smallest and the largest singular value and divide the two, and of course then take the absolute value of that, that's the condition number of the matrix. Bigger condition numbers mean less healthy matrix. It's more ill-conditioned. So we actually want small condition numbers. Let's go through some examples. Here's a matrix. What's the condition number? Notice now the first and second row are the same. So we would expect this to be very ill-conditioned and have a super high condition number. So I entered that in the MATLAB, calculated the condition number, and I get something like 6 times 10 to the 16. So that's practically numerical infinity. So this is a very ill-conditioned matrix, obviously. What about this matrix? Well, all the rows are pretty linearly independent, and we have a reasonably small condition number. I would call this a well-conditioned matrix. What about this matrix? The first and second row are not the same, but they're very close. This number is a little bit different. So the condition number here is around 10 to the 5. So that is not as high as this first one where we had 2 rows exact. We have 2 rows that are close, but a little bit different. So the condition number is a lot less. However, if we're solving this iteratively, that can still lead to problems. I would call this still a reasonably high condition number. Maybe not prohibitively high, but still reasonably ill-conditioned. Let's look at a final case. It's really the third case, but now the difference is even greater between the first and the second row. What condition number would this have? Well, we would expect this to be better conditioned than our third case. Let's see. Condition number, 10 to the third. So it's 2 orders of magnitude lower condition number. But, is that a high or low condition number? And it really depends on the algorithm we're solving it with and all that. But I would call this kind of on the threshold of being a reasonable condition number or not. We would like it smaller, but it is what it is. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.